Hello everyone, my name is Kendall Smith. I'm a computer science major from the University of Maryland, Baltimore County, and over the past 10 weeks I've been working on a research project at the University of Texas at Dallas under the supervision of Dr. Eric Wong, and the title of the project I'll be presenting today is Using Deep Learning to Detect Anti-Patterns in Software Projects. To begin, let's define what an anti-pattern is. An anti-pattern is a poorly designed solution to a problem in software development that decreases the maintainability of a software project. They can be both technical in the code base or organizational, which is involved in the way that a development team gets work done. My research is focused on technical anti-patterns that exist in code bases. They're also referred to as code smells or technical debt, but however they're referred, the core idea is when a solution in software gives up maintainability for functionality. Since we are in an age of agile code development, it is important that we make sure to keep up software maintainability with software functionality. As a result, developing tools that can detect anti-patterns automatically can decrease the cost of software maintenance in time, money, and man hours. This chart describes the four most commonly researched anti-patterns where researchers are using deep learning models for auto detection. Code clone is where identical or similar code is duplicated in a code base. As a quick example, let's say we're building some software for a scale, and we have two functions, one called get weight in ounces and one called get weight in pounds. These functions basically do the same thing, and they can be combined into a get weight function that takes a unit as a parameter. Feature envy is an anti-pattern where a method is more interested in the functionality of another class than its own class. They're also called misplaced methods because if you have a function that calls multiple functions of another class, it should probably be in that other class. Long method and God class are similar, just at different levels of abstraction. Where long method is a method with too many responsibilities, God class is a class with too many responsibilities. All of these anti-patterns lead to increased maintenance efforts through inconsistencies, testing challenges, decreased readability, poor cohesion, high coupling, and other factors. Throughout my research, I came across many different tools that are used to detect anti-patterns. These are traditional tools that do not employ machine learning or deep learning techniques. Instead, they rely on hard-coded rules engineered by the tool's creator. Despite their limitations, they are essential to the data labeling step of creating deep learning models. Even though this list is non-exhaustive, you can see a trend towards metrics-based tools that were developed primarily for Java. In the previous slide, there are traditional tools that can detect anti-patterns. So how can deep learning improve on the performance of what traditional tools already offer? First, let's define deep learning. Deep learning is a subset of machine learning that involves training artificial neural networks with multiple layers to recognize patterns and make predictions or decisions based on data. Deep learning models show potential in the research field because manual feature engineering is not required. This saves time for the developers of the tool. It can also help detect code smells and contexts that may have not been thought of by the creators of the model. Another benefit of deep learning is the potential of transfer learning, where we attempt to apply a deep learning model on source code of a different programming language. An example of this is we could build a deep learning model that's based on Java source code, and then if we had pre-processed the data in a way that is language independent, we could apply this model on C# source code and still get accurate results. This can help us build tools that are applicable to multiple programming languages and can help us with programming languages that do not have sufficient training data to build their own models. I came up with 3 research questions for my project. 1. Are there generalized relationships between certain types of anti-patterns? And if so, how can these relationships be used to improve current deep learning models? 2. What is the current state of transfer learning for anti-pattern detection across programming languages? And 3. What improvements can be made in current deep learning models to improve transfer learning capabilities? And there are two goals for my research. One, to analyze the current state of deep learning models for anti-pattern detection. And two, investigate the improvement of transfer learning both across programming languages and across code smells using the relationships between code smells. Studies, starting off with a systematic review of deep learning applications. This is mostly just background knowledge to things that apply to all deep learning models. Firstly is code representation. The different ways that code is represented in deep learning models includes tokens, trees, graphs, text, or metrics. And all models are actually either single code representations, meaning one of those that I just named, or hybrid code representations, which are a combination of two or more of those types. Metrics to evaluate deep learning models include precision, recall, F-score, or F-measure, and accuracy. Moving on to the relationships between code smells. The related study showed that domain is independent from intersmell relationships, meaning that the domain or the application of a software project has little to do with what code smells are co-located, meaning let's say we have software for a medical device and then we have software for some high-level business logic. Those domains and applications don't really have an effect on which different types of code smells are correlated. It's independent of the domain. It really just has to do with what makes up that code smell and how does that relate to what makes up another code smell. The related studies showed that there can be collocations amongst code smells that are proven statistically. There are code smells that are more likely to occur if another code smell is detected. The related studies mostly focused on code smells in the same class, with code smells in one class and another class not really having that much of an effect on each other. However, all of the related studies that I saw were done on Java code, which limits the generalizability of the findings, but they were consistent across studies. They did not contradict each other. All of the relationships found were either supported or not talked about because different smells were studied in different studies. One study explored the possibility of one code smell predicting another, where a model was trained for long method detection and used to predict future envy. It achieved 74% accuracy, showing that although related smells may not be a strict indicator of each other, there is a possibility for future extraction between related smells. I can only find one study that directly experimented with transfer learning. The study had an original model F-score between 0.52 and 0.64, with transfer learning between Java and C# code having an F-score of 0.40 and 0.50. These results suggest that transfer learning could possibly keep up with normal model performance with further research. To the left is a pie chart of the distribution of programming languages and a sample of deep learning smell detection research projects. It highlights the high focus on Java, with Java taking about 60% of the pie. And then the next majority, which is 30%, is actually shared by three different programming languages: C, C++, and C#. To the right is a chart that highlights the relationships found between code smells in multiple studies. I found no contradictions in the types of relationships found. Also, there's general agreement on what types of anti-patterns are related to each other. Again, you can see the focus on Java with all three studies favoring Java and Java tools for smell detection. There were three key findings from my research. The first was on the relationships between anti-patterns. We found that certain anti-patterns, such as long method and feature envy, often co-occur. This was proven statistically through previously looked at related studies. These findings can be used to improve model accuracy through improved feature extraction between code smells that have been proven to be likely to co-occur. The second is on the state of transfer learning. Although underexplored, initial studies suggest that transfer learning between languages like Java and C# show promise, with reasonable performance in detecting complex methods. Fortunately, to my knowledge, there's only one current study that explores transfer learning across programming languages. This calls for much more experimentation to be done on the topic. And third is about the challenges and opportunities in deep learning for anti-pattern detection. Their current focus on Java and existing studies highlights the need for developing language-independent models to broaden the applicability of deep learning techniques across different programming languages. The feature of my research includes 3 key points. 1. Developing a transfer learning model. Developing a transfer learning model to further push the boundaries of this research area is a key step, particularly between Java and C# because one research project has already shown promising results between these two languages, and if I can validate and extend those results, that would be very good for the field. 2 would be to expand language diversity in this research area, whether that be creating a model that's trained on a language other than Java, or if I'm using transfer learning capabilities to detect multiple different languages. And 3, improving data quality. Because anti-patterns are a nuanced topic and they require a lot of context, it's important that we have huge amounts of data to power these models. And if the data isn't available publicly, we may have to turn to data augmentation. But either way, improving the quality and quantity of data is very important to make progress in this field.